What's up, guys? So in this video, we are continuing development of our task scheduler RTOS. And in this video, I wanted to cover inter-task communication, where tasks communicate with one another. But before I get into that, I actually want to talk about something in the code. So within task 1, I just have this compare variable, and I keep incrementing it. And if you notice, I declare the variable as with the starter keyword. And the reason for doing this is because I want the variable count to maintain its value across multiple invocations of the function. And for this example, I only declare variable as static. It's only initialized once. And the value will persist between function calls. So once the variable is allocated in memory, subsequent calls to the variable will use the same memory location. So by declaring variables as static within our task, the task maintains the state information. If we want like variables to be shared between tasks, where each task could be associated with another variable, what we need to do is we need to introduce, a sort of message handling mechanism. So let me see how we could implement that. The way I'm thinking about doing this is to use like a global variable. And it's usually something that we avoid doing because if you have a lot of tasks that need to communicate with one another, I really want to avoid that approach because we want these variables to be accessed in an atomic, like an indulgent manner, because we want to prevent data corruption if we give simultaneous access to the variables. So let me implement a messaging inter-task communication method. Okay, so I implemented a global variable for inter-task communication. Now we have a volatile variable that we could update in between tasks. And what task 1 does is task 1 increments this variable. And then what task 2 does is when that variable data reaches a particular value, it toggles the LED connected, and then we set share data back to 0. So let's see how this function operates. And as expected, the LED toggles when it receives our message. Now, it's important when you're doing something like this that the task that is reading the shared data, that it has the same priority, or it has a higher priority than the task sending the data. I'll show you why. So suppose we have task 1 with a high priority, 10 tick counts, and we have task 2 with a priority of 20 tick counts, a lower priority. So let's run this program, and when we run this program, see the LED is stuck. The LED is stuck because what happens is that since task 1 has a higher priority than task 2, task 1 always increments the variable, and it does not allow the opportunity for task 2 to reset this variable back to 0. But if we set task 1 to priority of 20 and task 2 to priority of 10, the program will run as expected because now the task variable within the task is getting time to be reset. So that's something to keep in mind. Another thing to keep in mind with this particular application is that, remember, this is specific for the PIC16 devices. The reason why we could get away with doing something like this on the PIC16 is because, the PIC16 is an 8-bit microcontroller. And reading and writing an 8-bit variable, in this case a global variable, is an atomic operation. and we can't really interrupt that. Now, if you're using a larger variable, where it is that, let's say like a 32-bit variable, or unlike processors with wider data buses, you'll need to use a critical section of your code or, other type of synchronization methods so we can get the data integrity we're looking for. Usually within a, RTOS, we'd implement more complex communication mechanisms like queues and semaphores or mutexes. Maybe we will look at doing that, but in the next video, we'll look at improving our system even more. I hope this video was helpful. I'll help you one step closer to understanding how, we could implement a real-time scheduler on, a resource-constrained device like a 8-bit PIC16 microcontroller. That's it. Thanks for watching, and I'll see you in the next video.